Hello, everyone. Thank you for joining us for our webinar. Today, we are very pleased to have two leading experts in site characterization for DNAPL. We have Naji Akladiss and Dr. Chuck Newell, and it's really an honor to have both of you speaking today on our series. To give you a quick introduction, Naji is a project manager with the Maine Department of Environmental Protection, Bureau of Remediation in Augusta, Maine, and he currently serves on the ITRC Board of Advisors and is the former co-leader of the characterization and fractured rock teams. He's a licensed professional engineer in the state of Maine and a certified quality engineer by the American Society for Quality. And also, as a little side note, Naji is one of my favorite people of all time. So I'm delighted to have you here today with us, Naji.
Thank
Chuck
you.
is also phenomenal. Chuck is the vice president with GSI Environment. He has more than 30 years of experience, and I've heard Chuck speak many times. You guys are going to love to talk. He manages a lot of environmental engineering projects, and he's a member of the American Academy of Environmental Engineers, an NGAA certified groundwater professional, and an adjunct professor at Rice. So very busy guy. So we're delighted that you have time, Chuck, to join us. And you've got more subsurface characterization experience than most anyone in the industry. So I'm really, really excited to hear you guys talk today. So during the webinar, Chuck and Naji are going to discuss ways that we can evaluate the complexity of the subsurface geology. And we all know this is really critical for us to be able to improve DNAPL characterization and then to be able to effectively remediate any site that we encounter. So many of you who have attended before know the webinar today is being recorded and it'll be available on the resource section of the Microbial Insights website within the next week. And a link is automatically going to be emailed to all registrants as soon as it's available, so you can watch the recording anytime that you want as a refresher. And at the end of the webinar this morning, we're going to go through and answer any questions that you guys have, as many as we can get through before the noon time period. And if you have additional questions, you can enter them into the GoToWebinar software and we'll answer them at the end of the presentation. Or if you think about stuff after, you can always email them to info@microbe.com and we'll be happy to address your questions. So without anything further, I'm going to go ahead and turn it over to you, Naji.
Thank you, Dora. Again, I just want to emphasize that this course or this training is an ITRC sponsored training, and this training was originally 4-hour training, and we had to cut it down to 1 hour to accommodate the time frame we're given to present the entire training. Again, as Dora said, if you have any question at the end and we don't have time to respond to it, just email us a question or send it to Dora and we'll respond to you in writing. Okay, so the ITRC usually asks us to put this disclaimer up so we don't get sued. So this is a quick disclaimer. I'll give you a couple of minutes to read it. All right, you can have the PDF. Also, you can have the slides as well. So I'm going to talk a little bit about the ITRC. What is the ITRC? The ITRC is an organization hosted by ECOS. ECOS is the Environmental Council of State, which is all the environmental head of all the departments in all 50 states. So Commissioner or Secretary of the Environment and all those people, they get together, and that's the ECOS organization. And we are the technical branch of ECOS. The ITRC is a state-led organization, and all the teams and all the voting board member are state employee, and that's why we call it the state-led organization. But we do have partners as well. We do have Department of Energy, DOD, and EPA as partners with us. They join teams. They help us with document development and writing. And we do also have what we call industry affiliation program, where any member of the industry consulting firm can join the ITRC and become part of the team and help us with the documents. We also have academics, professors from schools and universities are also members of the teams, and they help us with document writing. And we also have stakeholders, member of the public that can join the ITRC to represent the public. What we do, we write documents on technology, approaches, contamination, or sites. And we provide technical and regulatory documents, and we provide training on those documents. And that's what the ITRC all about. And if you're interested in knowing more or joining a team, go ahead and log on the ITRC website and read some more about the organization. So we're going to talk about the problem statement. DNAPL, NAPL in general, is very difficult to clean. It's very challenging to deal with, and most likely provide difficulty in, and we don't have enough technology that can deal with that. But we do have ways of to characterize the site, and we're going to talk about that during this training. So one of the problems with the DNAPL site or NAPL site in general is very hard to achieve the cleanup goal. We cannot get to MCL easily. We can spend a lot of money, but we cannot eliminate the risk. The risk can stay at the end of the cleanup. And one of the common challenges with the DNAPL site is we don't understand them as well. It's not complete understanding of the NAPL site because we don't do good characterization. A complex matrix, either man-made or natural. And we set up an unrealistic goal. I can say, oh, I'm going to clean that DNAPL to MCL, and it's very difficult to achieve that. And quite often we select a remedy that does not work for the site. So what's the objective of our training today? We're going to be talking about how to understand the site conceptual model, typical for DNAPL dissolved phase plume. And we're going to also talk about fate and transport of NAPL in the subsurface. We are going to talk about the concept. What do we mean by integrated site characterization strategy? And at the end, we're going to talk about what tools available to us to be able to characterize the DNAPL site. And ITRC, the team, the DNAPL, the characterization team developed a tool table that have about 100 tools. And I think Chuck at the end is going to walk you through that table and show you how to use it. So here's an overview of the training. We're going to talk about NAPL characteristics. We're going to talk about life cycle and integrated site characterization. This is the subject of the course today. So NAPL, L-NAPL, usually gasoline product in general. And here's some example of it. Benzene, toluene, xylene, all benzene products are considered L-NAPL because it does float over water, have a lower specific gravity than water. And DNAPL, here's an example of DNAPL, TCE, PCE, and usually heavier than water and sinks and the sinker. Here's an example, the tube given us by Dr. Kurt Canal, and you can see PCE sinks down in the bottom of the tube, and N-hexane floats because it's lighter than water. We're going to talk about some of the NAPL property, some of the chemical and physical property of NAPL, and usually when we talk about those property, we discuss them, we give you equation, and we give you example how to solve those equations. But because of the short time frame we have for this course, we're going to maybe one or so, but we're not going to go over all the detail of all this property. So those property are density, viscosity, composition, solubility, volatility, sorption, and phase distribution. And we're going to talk about those semi-detail. So density. Density is mass per unit volume, and density usually expressed in milligram per liter, or it's a mass per volume, or can be expressed in terms of specific gravity. And specific gravity usually is the density of substance or chemical divided by the density of water and its unitless value. DNAPL usually have a specific gravity more than 1, which is heavier than water and usually sink, as I said earlier, and NAPL have a specific gravity lower than water and float on top. One of the things we need to understand that the property of the pure NAPL that you purchase from the manufacturer is totally different from the properties of the NAPL you have at your site. The reason for that, the pure product have nothing mixed with it. The NAPL at your site usually use already solvent, mixed with grease, with oil, and therefore the property of that NAPL is not the same as the one you purchase from the manufacturer. So you have to make sure you understand that when you go to the textbooks or books and look for solubility of some compound, that can change if you have it at your site. It's not going to be the same. Also, mixture. NAPL can exist in mixture, and DNAPL can partition in LNAPL. So you cannot, in some cases, you can see the DNAPL or LNAPL in a pure phase at your site. So you need to get a site-specific sample and check site-specific properties in order for you to know the property of the NAPL at your site. So the next property is viscosity. Viscosity is resistant to shear or flow, and viscosity is affected by temperature. As the temperature goes up, viscosity goes down, and the flow will increase. This slide here was put here by Chuck Newell, and I'm going to have him describe it and tell us what's all about this slide. Chuck?
Sure, Naji. So this is just a little anecdote, and this is about in the viscosity world, a very famous experiment in Australia, University of Queensland. 1927, they set up this experiment. You can see it right there, and you can actually see a webcam of this thing. And then they cut the stem in 1938. And then this is a very viscous solution. It's a pitch, which is coming from trees, but doesn't flow very much. Now, water's got a viscosity about 1 centipoise. So then 1947, the first drop fell. Then 1954 was the second one. I mean, this is an exciting experiment. So there's a lot going on here. And you can see that it's sort of taking more and more time as you go down. The last drop, the 8th one, fell in 2014. And Naji, do you think it's okay if we assign some homework to everybody out there who's attending the webinar?
Yeah. So if we heat this, we're thinking we're going to flow faster.
If we heat it, it would, but that's not the homework. I was just going to say the homework is everybody's got to go down there and watch the 9th drop fall. And then that might be somewhere, say 20, 30 or something like that. So we'd like her to do that.
Yeah.
But viscosity of, what's that, 230 billion centipoise? And so just very slow drop. So that's a viscosity example.
Mm-hmm. Thank you, Chuck. So the next property is solubility. Solubility basically the maximum amount of pure compound that can be dissolved in water at equilibrium. So we have NAPL here, that red figure here, and red is the NAPL, and above the NAPL is water, and the maximum amount of NAPL can dissolve in the water above it is solubility of that NAPL. Here's some example. We got a couple of examples for L-NAPL, benzene, and gasoline. You can see we have in molecular weight, density, and solubility, and we've got a couple of TCE and PCE example. And you can see that the density of the TCE is 1.46, and the density of the PCE is 1.62. Very heavy. It's heavier than water. And you see above it here the gasoline and benzene lighter than water. Okay, so we're gonna have a little exercise here. Usually I have much more math than this, but this is just one I left in the slide, just to give you an idea. If we have 55-gallon drum of TCE, how much water that 55-gallon drum have the potential to contaminate at to the level of MCL, which is 5 microgram per liter. So we're going to go through this exercise. 55-gallon, we dump them in a big lake, have unlimited amount of water. How many gallons of water will be contaminated above MCL? So here's the equation. 55 gallons, change that to liter and change it to mil, and then multiply that by the specific gravity of TCE, and give us how many grams of TCE. And then convert grams to milligrams, divide that by the MCL, which is 0.005 milligram, change it back to gallon, and we have 1.61 times 10 to the 10 gallon, which is 6 billion gallons. So if you have 55-gallon drum, you dump it, have the potential of contaminating 60 billion gallons of water above or at MCL.
So you got 60 billion liters, right?
No, gallon.
Gallon?
50, no, I'm sorry, 16 billion gallons.
Right.
Yeah, it's in the red about. Did I say 50 billion? No,
you're good.
16 billion. Yeah, okay, thank you. The next item here is, or property is solubility. And solubility, usually we use, if solubility for a pure product is different than solubility of a mixture. That's what I'm trying to say. So we use Rolt's law to figure this one out. So if you have a mixture in the subsurface, like you have TCE, PCE, and some other compound, to calculate the solubility of your mixture for any particular compound, you multiply the mole fraction of that compound by the solubility to come up with the solubility of that compound within the mixture. Is that clear? I assume it is. So if we have compound A, you divide that by mole fraction of compound A divided by mole fraction of compound B plus A plus whatever other compound there, multiply by solubility of pure compound A, it gives you solubility of that compound in the mixture. The next property is volatility. And volatility is very important in terms of vapor intrusion. The reason we need to know about volatility because of the danger of vapor intrusion in homes and businesses. So volatility, when it comes to a pure NAPL, As you see here in that figure, you have NAPL and you have vapor above the NAPL. So vapor pressure is a maximum amount of pure compound that can exist in the gas phase. And to calculate that, we use the ideal gas law. And here's one form of it. And this is another form of ideal gas law. And a third one that can give you the concentration of gas above the NAPL in the red. Again, I have mathematical example to try to solve it, but again, we don't have time for that for this training. Continuous volatility, if we're talking about water to air, we use Henry's law, and that helps us to find the amount of organic contaminant that will exist in gas phase in contact with water. And Henry's law is one form of it, is a unitless form of Henry's law, and here's a third one. And again, we don't have time to show you some example of that. Now, sorption. Sorption is dominated by soil organics or high surface area minerals. So if we're talking about absorption, it's basically the soil organic, and if we're talking about adsorption, that will be dominated by high surface area mineral. And this equation below here, it shows if you want to come with the concentration in soil, you multiply concentration of water times fraction organic carbon times the distribution coefficient for the organic carbon, and it'll give you the concentration sorbed in the soil. This is another example of how you can predict whether you have NAPL at your site or not. Traditionally, we used to use the 1% solubility rule of thumb. When the team was writing this document, we all agreed to stay away from this. This is not a reliable method. It can give you a false positive and false negative, and therefore the team decided not to use that concept and use what we call phase distribution instead. And phase distribution is, we do have a worksheet at the ITSC website to help you calculate whether you have NAPL at your site or not. And basically, you take a column of soil, you send it to the lab will give you the concentration of how much mass in that column of soil, and give you how much mass in the water, how much mass in the soil. And if you add the soil, mass in soil plus the mass in the water, subtract that from the total mass. If the total mass continues to be higher, then you have NAPL. If not, you don't have NAPL. And that worksheet was done by Kurt Pannell from Brown University. It's very handy tool you can use to find out. You just plug in the factors, and we populated most of the sheet was populated by all the properties we have for certain compound. You just put in the concentration you have in the column of soil, and will tell you whether you have NAPL or not. And I think Chuck have a story about how the 1% came about. Chuck, can you tell us a story about that?
Sure. It just this historical perspective. This was originally devised by the Canadian researchers who sort of invented this DNAPL paradigm back in the late 1980s, 1990s. I was actually working on a U.S. EPA DNAPL fact sheet, and in the beginning, John Cherry and his colleagues said, "Hey, use that 10% rule." And they had this because people didn't believe they had DNAPL at their site because they didn't see it. And then John Cherry and these other researchers saying, well, if you have high concentrations, that DNAPL's there. But I was reviewing it, and I originally wrote that 10% rule in my original guide, but John Cherry reviewed it, and he came back and just in his handwriting just said, hey, we've done some more thinking about this. We think it's better to use 1%. So that's just a little bit of the history. It was sort of developed for a different purpose. Hey, DNAPL can be at these sites. You got to be aware of it. But then over time, we've been realizing there's these other sources like matrix diffusion. And now we're thinking this just may not be a good rule.
Okay, so the best way to do it, as we said, is phase distribution, and this is the equation, and there is more information about that at the ITRC website. So some other property is interaction with the subsurface media effect that does affect mobility, and those 5 properties here: interfacial tension, wettability, capillary pressure, saturation, and residual saturation. I don't think we have time to go over those, but I'm going to talk a little bit about saturation and residual saturation because those are the 2 more applicable kind of mobility of the DNAPL in the subsurface. The other ones are important as well, but we only have time for these 2. So what is saturation? Saturation is what proportion of the subsurface pore space within certain volume you select occupied by fluid, and that fluid could be DNAPL, air, or water. And it's a number between 0 and 1. The residual saturation is the same volume of soil, but what fraction of that volume that's been separated from the original DNAPL and become disconnected from the DNAPL. And I'm going to describe that in the next slide. Here's at the top the figure is the what we call residual saturation, which is big blobs of DNAPL disconnected and not connected to each other, and that mostly not mobile. It was not going to move. The figure below it is you can see that DNAPL is all connected and all continuous. So that DNAPL have, if we have enough pressure head, that DNAPL have the potential to move and become mobile and move from one spot to another. We're going to talk a little bit about the life cycle of DNAPL. So we're going to start with the classic model. You have a source zone, you have a spill. You can see here where it says active source, that something is spilled there. The DNAPL is going to go down. I'm going to migrate down to the subsurface and go through the soil on top of the water, and then it's going to continue. If it hits low permeability zone, it will go around it and keep going down until it gets to the area where it's not going to move anymore. But some of that DNAPL or DNAPL is going to dissolve in the water and going to move in the aquifer and become dissolved plume. So here's another kind of picture of it. So we see in this picture some of the DNAPL or DNAPL going to evaporize as a vapor, going to come out as a vapor. Some are going to dissolve in the plume and going to move with the plume. Some will settle down in the bottom of in the aquifer, and if there's enough head pressure, the DNAPL will displace water in the pool space, and it will settle in the pool space and will displace water. So this is basically, so you have DNAPL go as vapor, some dissolve, and some will settle in the pool space. One of the issues here, the subsurface is very heterogeneous. The pore structure in the subsurface and the capillary pressure can change from area to area within very short space, within inches. you can have a different pool structure and capillary property. Therefore, you need to understand that the subsurface is heterogeneous and the flow is not going to be the same from one zone to another because of the pool structure can vary from area to area in a very short distance. Again, secondary source within the groundwater plume. We always look for DNAPL, we always look for the source, we always look to see where the DNAPL gets spilled, where is it, we cannot find it. Quite often we cannot find the DNAPL because especially in the late phase, the DNAPL already moved on, and what we see is what's sorbed in aquifer matrix or back diffused from the low permeability zone. So after the DNAPL moved from the source area, you still see high concentration of NAPL in the plume, and you always wonder, where is the DNAPL? It's not there anymore, but the back diffusion process can introduce more contamination to the aquifer. Here's an example. Early stage, you see this. You have a semi-sandy, permeable area, and lined up by very high, low permeability zone below that sandy area. So you have the plume in that pool early stage. You can see it in the top left in the top figure up there. And at the molecular diffusion will take place and the NAPL will diffuse in the low permeability zone. And then the lower picture, the late stage or late time when the NAPL already moved, the NAPL diffused in the low permeability zone, start back diffuse back in the aquifer and maintain the concentration to be high concentration in the aquifer. And that's what happened. We cannot see the NAPL anymore, but that back diffusion process take place and make the plume longevity continue to be contaminated for longer period of time because of the back diffusion process. So here is a video, and I'm going to have Chuck talk about that video quickly. Chuck, take it over.
Okay, I think maybe it's on the next slide. Is that right, Naji? Or
here we
go. Okay, so developed by landowner. She's the grad student, Dr. Tom Sale of Colorado State. Here's this research tank. It's filled with sand, but more importantly, 4 of these clay lenses, A, B, C, and D. And Leanne sets this up, and then they're going to start and set this green dye from right to left, and there it is. So that's advection. That's just groundwater flow, and the counter, that's 6 days, that's 7 days. And so this is just the way a plume works. It's coming from a source on the left, and it's flowing, and that's your plume. But then you can start looking at this carefully, particularly that second from the top clay unit. You can see some of that, well, that boundary is getting green. Then at day 23, they stop that source, and that sand, it cleans up really, really quickly, just as you'd expect. And that's what a computer model will tell you. 2 or 3 flushes, that sand is clean. But here we are on day 36. This is 14 days after they stop that source. They're still green in this picture. And where's it coming from? Well, it's coming from this green dye that diffused into these clays. And when the sand then cleaned up, it's now diffusing back out. And so it's day 55, and landowner's coming in and saying, Dr. Sale, can I stop? No, keep going. And she's taking these pictures every day. And the deal is they run this thing for, right now we're at 68 days. They run it for, I think, 123 days, and there's still this material in there. So just a really, Tom Sale says this is perhaps, the best demonstration of matrix diffusion, better than any of the great papers he wrote, but this is how we explain it. So that's what I've got, Naji. Let's move on.
Thank you. So the team have developed this, what we call the 14 compartment model. It's basically a model to show how the contaminant or mass can move from one phase to another, okay? And if you look at here, you have the various phases on the left: vapor, DNAPL, aqueous phase, and soaked phase. And on top, you have source zone and you have the plume. And you can see, for example, the first arrows go from NAPL and its dashed line, and can go from DNAPL to vapor phase or from DNAPL to aqueous phase, but it cannot go back. So dashed line means it will go one way, but does not go the other way. The line, the arrows next to it, you can see the aqueous phase can go to vapor phase and can go back to aqueous. So the arrow have two heads. And it's just in general, this is a model to show you where the mass can move back and forth and where it cannot move back once it goes forward to a certain phase. So I'll give you an idea. If you're losing mass, you could have lost mass to vapor, you can have lost mass to aqueous, or you can have lost mass because it was sorbed in the soil. Okay, so continue with the life cycle. Early stage, we have that traditional or classical spill. The water, the DNAPL goes down, and the 14 compartment model again below. And you can see at the early stage, as the NAPL goes down in the low permeability zone, you have very low mass in it, but they have a lot of mass or moderate amount of mass in the transmissive zone. And in the plume, the low K zone still does not have as much mass in it yet because it has not got there yet. But the aqueous phase have a moderate amount of mass. If you go to the middle stage, where the DNAPL now have enough time to occupy all the stages, it's DNAPL everywhere, okay? So you see in the middle stage, you see DNAPL moderate amount in all phases. The late phase now, in the late stage, you can see the NAPL already have moved from the source, already have moved from the plume, but it lingered behind in the aqueous and soaked phase in the source as well as the plume. You still have moderate amount because the soaked phase will continue to feed the plume, so you will have continuous NAPL or contamination going to the plume in the late stage in the aqueous phase and soaked phase. So from here, I'm going to turn it over to Dr. Chuck Newell, and I'm going to take the slides from here.
Thanks, Naji. And just checking in, can everybody, I've been made the presenter. I'm going to show my screen. And now how does that look to everybody? Can we, Naji, can you see my slide, my screen? Mm-hmm.
Well, I'm still seeing my screen. I don't know if Dora can tell me what to do to see your screen, but I can follow your slide because we have the same set anyway.
I can see your screen, Chuck. It looks good, and I can hear you clearly, so you're good to go.
Great. Let's go. Okay, now we're going to talk about what I call the journey is the reward. This process, this integrated site characterization process, on how you take all the sort of the technical knowledge that Naji talked about, and we're going to talk about a plan. How do you select tools for characterizing that DNAPL site, and then the implementation of it. So what we're going to do is that there's sort of this new paradigm on how sites work, all this new concepts regarding matrix diffusions and things like that. That heterogeneity is really important, the geologic heterogeneity. I call it the revenge of the geologist, that we've got to start thinking about where these contaminants can diffuse into low permeability units. That anisotropic conditions replace isotropic conditions. It's not a uniform geology down there. This is a key one. That diffusion is really important, and it's supplanting the dispersion that we used for a long time, thinking that was the key, one of key transport processes. Back diffusion can be a significant source, just as DNAPL can, and it becomes more of a log normal world than a bell-shaped world, and than a Gaussian distribution, and that things are in dynamics. Stuff's diffusing into clays, it's diffusing out, and that replaces sort of this steady state condition. Okay, so then we're going to talk about this integrated site characterization, and it's a process to improve the efficiency and effectiveness of site characterization efforts at NAPL sites. We want to get sufficient resolution of data. We want to understand what controls these controlling heterogeneities and how they affect distribution, fate, and transport. And we want to get this integrated three-dimensional conceptual site model that incorporates all this stuff so we can understand much better what this fate and transport, how it works at a site. Okay, so the key goal here is we want to develop a conceptual site model with significant depth and clarity so that risk can be accurately assessed and appropriate remediation strategies be developed. So we're trying to get this conceptual site model. Where did the stuff get in the ground? What happened to it? What are the processes that are affecting it? Okay, now the key thing when the team really worked on this is this concept that you have to come up with objectives-based site characterization. And this emphasizes that you have to have these clear, effective objectives that drive the data collection in here. Now, it's systematic, it's a stepwise process that encourages things like systematic planning, dynamic work strategies, getting the information out there, and then real-time measurements so you get these fast sort of feedback loops, and you can sort of see this. So the document really focuses on this process. And you're going to make these objectives, and you're going to go out and get that data, and then you're going to figure out what your conceptual site model really, really looks like. Okay, so now here's just the different pieces. There's the planning, tool selection, implementation, and the planning and module's got these 4 steps, and so we're going to talk about that. But this is an ITRC document, right? So it's got to have one of those dang flow charts. So yep, here it is. So here's this flow chart, and we're going to keep coming back on this. This is this process that you're going to sort of use all this new fate and transport knowledge. We're going to be thinking about matrix diffusion, and we're going to define the problem, identify the data needs and the resolution, develop these data collection objectives. So I want to know X. So how do I do that? And then you're going to design a data collection analysis plan to answer to meet those objectives, to get that key information in there. So that's the planning part, the first 4 steps of the flow chart. Then we're going to select tools. There's this detailed spreadsheet of these tools that we'll show you. And then you're going to implement this thing, actually put it out in the field, and update this conceptual site model. Okay, so let's do step 1, define the problem, assess CSM uncertainties. So we're going to figure all this stuff out. And for this, I think we go to this dry cleaner site. And so this is the example that the group came up with. It's a commercial industrial location, pretty shallow groundwater, 20 feet, 6 meters. Right now, 5 monitoring wells are out there. There's 18 soil borings. There's no soil gas. Maybe there's been some of this treatment that's in there, but there's quite a bit of uncertainty about, what is the real picture here? And so we've got to sort of figure some of that stuff out. So, for example, we don't know what the down gradient situation looks like. If you look on the bottom right of that thing, groundwater flowing sort of to the bottom right. There's no wells out there that are non-detect. The source area is infirmed. We're not sure it's really there. There's no soil gas in there. There's been no evaluation of this. So we got to do better than that. So step 2, identify the data needs and the spatial resolution. And we're going to translate those questions we have about the site into these data needs, and then determine the resolution needed to assess these controlling heterogeneities, that key geology stuff. So here's something about the resolution. This is from Seth Pitkin. I really like this a lot, that you can have different pixelations in here. And this is like maybe a spy satellite getting better over time. And then, eventually they can read license plates from space. But it's the same for us, is that if you only have a few monitoring wells with 10-foot screens, that's not very high resolution. But the more data points you get in there, this picture can crystallize in front of your face and you can really see it. Okay, so step 2, we're going to need, let's start thinking about some of this stuff. Additional groundwater samples are needed to find that plume extent and see if that boundary really works. Additional soil samples to really say, where is that source mass that we're going to go in there? We got these residences and the apartments, we've got to do some soil gas stuff here as well. So that's step 2. Let's go in here. And then there's also this vertical part. And if you look in here, the blue is sort of where some of the soil borings were done. And there's if you do this cross section from left and right, but then the pink, we're not really sure what's down there. We need to go in there and look underneath there and see what's going on. Okay, so that's identifying our data needs and what resolution we need. And then here's this thing, then we got to write down, we got to formalize, this is a contract to ourselves, what are these data collection objectives? They got to be specific, they got to be clear, they got to be actionable. It's not just, I want to understand exactly everything about the site. I want to know exactly where that 5 microgram per liter contour is down gradient, for example. I want to know if that source zone is deeper than what we think it is. We're going to consider data types, quality and density, and the resolution of all this stuff in this process. So we're marching down that flow chart, and we're sort of still in the top part, but in our mind, we're starting to get this plan together. Okay, so here's some examples of data collection objectives. We want to do groundwater grab samples at X and Y depths out there. We want to this is for delineation of the extent of that plume. We want to do soil borings every certain number of feet to capture that subsurface variability. Delineate to groundwater standards, 5 microgram per liter MCL. Okay, let's start with installing 3 to 5 wells. We're going to monitor along the axis of flow. We're going to monitor quarterly for 2 years, evaluate concentration versus time, concentration versus distance. We're going to get COCs and geochemical parameters. Hey, we're going to, maybe this is some natural attenuation stuff maybe we're going to be thinking about. Okay, so that's step 3. Then we do this data collection analysis plan. We're going to write the work plan. We're going to recognize limitations of our data. We're going to select some sort of data management tools and then develop this data management process. And here the group says, really think about some real-time analysis, because if you're out there and you've got this on-site lab, you can do these feedback loops get really quick, and you can get more done for less money. And then there's a screening method. You fill in the gaps, you map the extent. So that's this consideration there in step 4. So generally 3 types of data are collected. There's sort of quantitative tools that provide actual numbers. It's this many micrograms per liter. It's this many micrograms per meter cubed per vapor, okay? Then there's semi-quantitative, and it's stuff that, it's not really the key concentration units, but it may be something like a MIP, that sort of gives you some other reading that's coming out of there. And then finally, there's some qualitative that is this indirect measure. They talk about this PID or something like that provides a relative measure of absence or presence, but it alone, you can't use that to compare against standards or things of that nature. But all 3 things have their part in here, and you can sort of see what's going on, and it can help you figure out that conceptual site model. We're interested in accuracy and precision, how close a result comes to a true value. That's the accuracy, and that's where you can sort of get close to that bullseye. And precision is just, if you keep doing this over and over again, what is that concept? And Naji's got a background as a quality control engineer. This is sort of close to his heart, but this is talked about in the design document, so you understand how accurate your readings are and then how precise they are to sort of understand where you are standing in this statistical world in here. So number 4 is we're going to design this data collection analysis process, get this work plan. It should be dynamic, flexible, and adaptable. It's going to work for large sites. Some of the stuff we've talked about, field laboratories are good, real-time data collection, and you adjust this thing to address these data gaps. So going back in here, here's this updated plume area. We've done these borings. We've done these groundwater grab samples. 3 for boring. We're actually taking some of this data from sort of a direct push in there. And then now we're getting some of the sort of a clear picture of what's going on here. We've got this updated groundwater plume area. And so this is our design of what we're going to do and get this stuff out there. Then in soil gas, we're going to do soil gas at these locations and get an idea of what the vapor plume looks like. Okay, so now we've done the plan, and now we're going to select the tools. So we're going to sort of give you a little bit about the tools matrix, the framework, this functionality, case studies, and then we're going to talk about all these things are in here: vapor and soil gas, solid media, the geologic media, direct push tools, discrete groundwater sampling, DNAPL presence, and chemical screening. So this thing is big. It's got a lot of stuff in it. You can download this spreadsheet. And they're broken into different categories and subcategories. You can see the tools here. There's geophysics, hydraulic testing, vapor sampling, geologic media, direct push, DNAPL presence, on and on. And so this thing is out there that you can look and say, I want to look at tools to answer my question. What are my options in here? So it contains over 100 tools, and you can look at this. They're sorted by all these different. You can sort them in different ways by geology. You know, is it fractured rock or consolidated? And it's ranked by data quality. Is this quantitative, semi-quantitative, or qualitative? And now you can start saying, oh, I'm going to start culling these out and seeing which ones are going to help answer my problem. And then here's just some more looking at this spreadsheet. Here's these sort of surface geophysics. Here's the subsurface, the zone, the geology that it works on, some of the different things, the information that it will give you are the green boxes. You click on any box for a description or a definition, and you got all this text that group worked so hard to develop and let you know. Okay, so here's Appendix D, you know, groundwater penetrating radar. This is the type of information you come up with. And this just is trying to expand your world so you can really get this description, applicability, limitations of all these different characterization methods. Okay, just another view in here, the shaded boxes. That green says, yeah, it meets these objectives, and that this is a tool that potentially you should consider to do this stuff. Okay, so we're going to do our case example. We're going to delineate lateral and vertical extent of dissolved phase plume. Our goals, you know, where is that boundary of the plume? How are we doing in terms of this remediation? And what's the story on vapor extraction? We're going to filter by chemistry, concentration. It's unconsolidated, it's saturated. And then here we put that stuff in there and we start seeing, oh, these are the things on the left, these different examples that we might consider to help answer some of our questions after we apply these filters in there. And so here's the tools, and this is sort of the information you get. And you can see on the green boxes which tool is giving you what type of information in here. So just sort of feeding up, this is all the ones that you might consider in here in terms of different devices that sort of that sort of meet the goals or might be able to help you answer your data collection objectives. Okay, so the search in this case returned 21 tools, and then we want to expedite the assessment. So we're thinking now, based on that, let's do direct push borings. We're going to do the active soil gas survey. And we got this mobile lab out there to get this fast turnaround, this fast feedback. Okay, so the matrix summary, it's an objective selection of tools. There's over 100 in there. It helps you do this selection process, evaluate the results, align the data gaps, and you repeat until those objectives have been met. Okay, a couple slides about implementation. And this is at the very bottom. We're going to implement the investigation, perform this data evaluation and this interpretation. And finally, here's the real gold behind all this, update that conceptual site model. So now we had these yellow triangles before. We're going to look here with these different characterization tools. And now we start seeing here where this is the soil and groundwater data, which ones exceed criteria and which ones do not. So now we're starting to get some of the color in this and understand green versus red in here. So this is the PCE milligram per kilogram from the mobile lab. And so we're getting some of the data, for example, on here. And now we've got this sort of new soil and groundwater, this data, this new interpretation where we have the results exceed this criteria. And then we've got a couple of clean lines. Note, we still don't have that clean line on the bottom right of the graph. So that's, this is iterative. We have to go back and look at this. Source area concentrations remain elevated. And so more work has got to be done. So we got to update this conceptual site model. We're going to put in there the data from all phases of the project. And then, as it progresses, the data needs are going to shift. And then the questions get narrower as you sort of go through more and more of this iterations to update that conceptual site model. And that conceptual site model will evolve over time. So here's this new picture that we're looking at. the screening levels for vapor, the soil criteria, the groundwater criteria, and then we're sort of got this picture of there's the vapor right here. Here's the sort of some of the groundwater stuff, and then here we look down below, and so we've got a better vertical picture of what's going on. So this is our update of the conceptual site model. So the benefits from this, it confirmed, hey, you need to do this indoor air stuff. There are some issues out there. We optimize our data density in specific areas. We determined the source zone remediation target area and saved quite a bit of funding in this example in terms of using this approach to characterize your DNAPL site. So to wrap it up, here's that flow chart: planning, tool selection, implementation, and then thank you for participating. Naji, anything you wanted to add?
No, you did a good job. Covered it very well.
All right, thank you, Naji. Thank you, Chuck. We'll just do one or two questions, and then what we'll do is, because we're short on time, if you can email any additional questions that you have to info@microbe.com, we'll compile a list of these questions and get them over to Naji and Chuck to answer, and then we will send out a PDF of their responses to everyone that attended today. But a couple questions that I think are really quick. Naji, you showed that DNAPL calculation spreadsheet. Is that available somewhere online?
Yes, if you go to the ITRC website, click on DNAPL and look at the integrated DNAPL guidance document, the spreadsheet is part of that document. You can download it, you can use it, you can play with it. As well as the tool table too. Yeah, it's very, very good tool.
Pretty good. And you put in your site information about your say a soil sample, and it will tell you if there's enough room in just the aqueous phase, the vapor phase, and the sorb phase to account for all that mass. And if you count for all the mass in those different phases, then it says, oh, there has to be DNAPL there.
If you send me your email address, I do have it here on my computer. I will send it to you.
Great. All right, one more quick question, Chuck. Can you talk about the DNAPL pools? I know we mentioned them a couple times. Have those been documented in field settings or only shown in conceptual places only?
DNAPL pools? Yeah. So the original thought was, this is early on in the business, is that there were these DNAPL pools out there, and they turned out to be very rare to find. And I've worked on a couple of sites where there's enough DNAPL that it accumulates and you could pump a little out. But it is really rare. And the conceptual model changed that at many sites, this DNAPL went down, and it's got this low viscosity, and these fingers spread out everywhere. And then they will start to melt, and actually melt's not the right word, but dissolve, and then diffuse into the clays and go away. So that's this idea. There's these old studies that you only find the DNAPL in a small percentage of the sites, and so this idea that there are a lot of DNAPL pools out there is probably not true. It's only on a couple of these really big sites with the right conditions.
All right, great. All right, well, thank you, everyone. Naji, did you have a title slide that showed the contact information for you and Chuck, or Chuck, do you have one that would show your email?
Oh, I didn't.
I don't think we do.
I'll send that. I'm sorry. I usually have the title slide and my contact information. How can we resolve that, Dora? Should I send it to you and have it available?
Yeah,
whoever asks for it?
Can you add it to the cover on the PDF when you make the PDF of the slides, and then we will send that out to everyone so that you'll have their contact information?
Okay, we'll do that.
All right, wonderful. Well,
Okay.
Thank you so much, Naji. Thank you very much, Chuck. It was an amazing presentation. We do have quite a few questions, so again, we'll put those in a Word document and shoot them over to you guys to get the answers. And everyone, we really appreciate you taking time out of your busy schedules and attending. We're very grateful to have your participation each month in these webinars. Toward the end of the month, we do have Kurt Pinnell and Natalie Capiro who's going to be speaking for us as well. So some exciting webinars coming up in the future. So stay tuned for some ads, how to register for that. And again, if you have questions, please email them over to info@microbe.com. And thank you again, Chuck. Thank you, Naji, for being here today. We really appreciate it.
No problem. Thank you.
All right. Thank you, everyone.